This is a car that can fly on the ground, reaching speeds of up to 600 kilometers per hour. To put that into perspective, a commercial airliner flies at about 800 kilometers per hour. This is one of the greatest representations of cutting-edge human technology, the magnetic levitation train, or Maglev train. So how does it actually work? We all know that traditional wheel-rail trains operate through rolling friction between the wheels and the tracks. However, this friction is exactly what limits our ambition to achieve higher train speeds. Maglev trains, on the other hand, eliminate mechanical contact and friction entirely. With no friction to limit it, the train can reach significantly higher speeds. The basic principle behind it isn't too complex. It's all about electromagnetic force. Take, for example, the world's fastest superconducting maglev train. Along both sides of the train are multiple superconducting magnets that are cooled to extremely low temperatures using liquid helium. These superconducting magnets have no electrical resistance. So, once they are energized with an excitation current, they can maintain a circulating direct current indefinitely, with no energy loss. The electric current flowing through the superconducting coils is massive, up to 700,000 amperes, generating an incredibly powerful magnetic field. You can think of each coil as a super strong permanent magnet. 4 superconductors form one unit, with alternating current polarities. Let's first look at how the train moves forward. On both sides of the track, a series of conventional electromagnets called propulsion coils are installed. The magnetic force they produce interacts with the magnetic field on the train. According to the principle that like poles repel and unlike poles attract, this interaction generates both thrust and pull, pushing the train forward. When the train reaches the next appropriate position, the propulsion coils switch their polarity again, generating a new forward force. By controlling the current in the propulsion coils, the train's movement and speed can be precisely controlled. This is known as the switching frequency, which determines the train's speed. Essentially, it works on the same principle as an electric motor, but with the electromagnets and permanent magnets spread out in a straight line. This is why it's also called a linear synchronous motor. Now, how does the train levitate? The levitation mechanism is both clever and fascinating. On both sides of the track are a series of figure-8-shaped coils. The amazing thing is that they don't require any external power to function, yet they can levitate the train. To help you understand, imagine the superconducting magnets on either side of the train as one large magnet. As the train moves parallel to these figure-8 coils, the coils cut through the magnetic field. According to Faraday's law of electromagnetic induction, voltages are induced in the upper and lower coils, appearing to be in the same direction. But when we analyze them more closely, we find that the voltages are actually opposite in direction. This means that the net voltage is 0, no current flows, and therefore, no magnetic field is generated. However, if the superconducting magnet shifts slightly toward the bottom coil, the magnetic flux through the bottom coil increases, generating a greater voltage than in the top coil. This results in a current loop. This current creates a south pole in the top coil and a north pole in the bottom coil, applying an upward force on the magnet. When this upward force exceeds gravity, the magnet rises. The faster the train moves, the stronger the lifting force becomes, until it balances with gravity, and the train levitates. Now, how does the train stay centered on the track without hitting the side walls? Engineers solved this by interconnecting the figure-8 coils on both sides of the track. For example, if the train shifts slightly to the right, a voltage difference arises between the left and right coils. This causes a current to flow through the interconnected coils. This current flow alters the magnetic field in a way that generates a restoring force, nudging the train back to the center. Thanks to electromagnetic forces, the train is no longer constrained by friction. That means not only can it travel incredibly fast, but the passenger experience is also much smoother and quieter, thanks to the frictionless and stable levitating motion. If you enjoyed this breakdown, hit that like button and subscribe for more awesome tech stories from the future.